And we'll start. Alright, so first things first, I'm going to quickly review Riemann sums. So Riemann sums are a way we can estimate the area underneath the curve. If I want to do a left-hand Riemann sum, so here's y equals x over 4 that I'm graphing right now. If I do a left-hand Riemann sum, then I'll get my heights from the left side, so starting at 0, and then 1/4, and then 1 as we go up. And we will underestimate with the left-hand Riemann sum as long as our function is increasing. We'll overestimate if we're decreasing. With the right-hand Riemann sum, the opposite happens. So I overestimate if I'm increasing and underestimate if I'm decreasing. Right-hand Riemann sum for this one would start with the right-hand side. So my first rectangle would have a height of 1/4 and second would have a height of 1. I can also do a midpoint rectangle. So in this case, we would get our heights from the midpoint. Instead of getting my height at 0 or height at 1, I would get my height at 0.5 and use that for my entire rectangle going all the way up. So height at 0.5, height at 1.5, height at 2.5. If I plug in 0.5, that's 1/2 into our equation 1/4 x squared. And I get 1/2 times 1/2 is 1/4 times 1/4 is 1/8 is my height of the first rectangle. Any questions on anything we've done with left, right, or midpoint Riemann sums? Okay, so it gets a little bit trickier when we start talking about trapezoidal Riemann sums. So here I've got, one more time, y equals x squared over 2 plus x plus 1 with a bunch of heights plugged in here. If I get a left-hand Riemann sum, then my first height has a height of 8.5, and I keep going from there. If I get a right-hand Riemann sum, then my first height would have a height of I'm going from 5 to 3, I'm doing 4 rectangles. Okay, first height has a height of 2.5 then. If I do a midpoint Riemann sum, then I'd have to get my height from the middle, which is at -4, which would be a height of 5. If I did a trapezoidal, trapezoidals would get both heights and create trapezoids out of them. So I would take my height at 8.5, my height at 2.5, and get the average of those two heights, and then multiply by my base of 2 to get my area of this trapezoid. So that would be 8.5 plus 2.5, which is 11 divided by 2. So I'll end up with 2 times 11 divided by 2, or 11 for my total area of this trapezoid. Any questions on our areas for left, right, midpoint, or trapezoidal, the harder one? All right. So then breaking out of this, we also have infinite Riemann sums. Infinite Riemann sums take this basic idea of multiplying a base times a height and make it into a general equation. So in this case, if I want to make an infinite Riemann sum for a right endpoint rectangle, then I could create my height as my function of my start point A plus some iterations, that's a number that starts at 1 and goes up for forever, times dx. So this would be my height at my start point plus my change in x, which is my total distance, start point to end point, divided by my number of rectangles, times I. Okay, that would give me my height at the right side, times my base, which is my start point minus end point, divided by my number of rectangles, would give me a base times height is the area of our rectangle. Putting it all together, it would look like this. Okay, I'm taking the limit as n, the number of rectangles, approaches infinity, from 1 to infinity of our function of our start point plus our change in x times iteration, times b minus a over n. Okay, then we can use summation formulas. So these are shortcuts for adding iterations from 1 to infinity together to plug in and get our answer for an infinite Riemann sum. Okay, double check. I think I've got Kyle. Do I have Nikita in here yet? Okay, I've got Niall, Andrew, and Kyle, it looks like. Any questions on what's going on with our infinite Riemann sum formula first? Okay, if not, I'm going to jump down and we'll do one. So using our infinite Riemann sum formula. Okay, you can hear something in the background. It might actually be my echo. Okay, I've got Sarah in now. Any questions on the infinite Riemann sum? What's going on with the formula? Alright, so here's one example of how that could work. So we're finding the area underneath x squared from 1 to 3. So from 1 to 3 with infinitely many rectangles, our n number of rectangles would be infinity. Our distance between our start point and end point is 3 minus 1 or 2. So my change in x is 2 over n. My height would be my start point 1 plus my iteration, so that's starting at 1 and then going to infinity, times our dx, or 2 over n. So for the first rectangle, I is 1. I'll start at 1 and I'll go over by 1 more 2 over n, so 1 more infinitely small space, and then I'll plug that into my equation to get my height. So when I plug it into my equation to get my height, we square it. So if I square 1 plus 2i over n, so this is a plus b squared, I should get a squared plus 2ab plus b squared. So that's 1 squared plus 2 times ab would be 4i over n plus b squared. So 2i squared is 4i squared over n squared is n squared. So if all of this is my height, we can multiply by our base of 2 over n. And when I multiply by my base of 2 over n, I'll end up with this. This is after I distribute. Okay, now I've really got 3 different sums here. So three different sums. 1, 2, 3. Because this is a summation, I can split these up around any plus sign or minus sign. So I'm going to do that. If I split this up into 3 separate summations that we're doing right now, then I can pull out anything that is constant, and then take my limits. So right now, for each of these summation formulas, if I take my limit as we approach infinity, then I've got our limit as we approach infinity of 2 over n times 1. My summation formulas for a constant, if I scroll back up, for a constant would be c over n. For an iteration would be n times n plus 1 over 2, and for I squared would be n times n plus 1 times 2n plus 1 over 6. So with those substitutions now, Cn, so that's my constant times my number, would end up with 1n. I would end up with n times n plus 1 over 2, and I squared is n times n plus 1 times 2n plus 1 over 6. Okay, then we simplify according to our limits now. So for this first term, my n and my n cancels, and my limit will become 2 for this term. For my second term, I've got 8n squared plus 8 over 2n squared. So my general limit, as we approach infinity, would become 8 over 2 for the constant of my coefficients, would be 4. For our last one, my largest power would be 8 times n squared times 2n, which is 16n cubed over 6n cubed. Gives me 16 over 6, or 8 thirds. When you add all of that together, we get 26 thirds. So the area underneath the curve of x squared from 1 to 3 is 26 thirds. So this is really what we're doing when we integrate. If I integrate x squared in terms of x from 1 to 3, I would get x cubed over 3 from 1 to 3. Plug in your upper bound, so that's 27 over 3 is 9 minus our lower bound of 1/3 would give us 27 minus 1/3 is 26 thirds. So 27 thirds minus 1/3 is 26 thirds. Any questions on what we did here? I'll zoom out a bit. Okay, going once, going twice. Okay, I'm going to jump back really quick for Sarah. So for Sarah, one more time. Here I've got y equals x squared over 2 plus x plus 1 from negative 5 to 3. I've got a table of values showing all possible y values from negative 5 to 3. What I'm going to do is I'm going to split this up into 4 equally spaced rectangles. So if I split this up into left and right Riemann sums, then I would get my heights of these rectangles from the left side. So here's my heights from the left side showing. So my first height would be from the left side of 8.5 for a base of 2. So my first rectangle would give me area of 17. For my second rectangle, I would go from -3 to -1, so that's another base of 2, but I would take my height at -3, that's my left side. So my rectangles right now look like this, with heights from the left side for each one. So 8.5 by 2, 2.5 by 2, 0.5 by 2, and 2.5 by 2 to get the areas of all of these spaces. Sarah, any questions on left-hand Riemann sums? Okay. Right-hand Riemann sums do the same thing, but from the right-hand side. So if my heights are from the right, then my first rectangle is going to have a height of, since I've got a base of 2, my height would be from 2.5. So I'd have 2.5 by 2, or a height of 5 for my first rectangle. Okay, if I want to do this as midpoints, then I would get my height from the middle instead. So first rectangle is still from -5 to -3, but this time I'm going to get my height from the middle. So my height will be 5. 5 times 2 is 10 for the height of the first rectangle. Any questions on right-hand or midpoint Riemann sums? All right, last one, trapezoidal. For trapezoidal Riemann sums, instead of making rectangles, we make trapezoids. So my first trapezoid is from -5 to -3. I've got 2 heights this time at 8.5 and 2.5. So when I add those 2 together, I would get 11. To get my average, I'd divide by 2. So 11 divided by 2 times our base of 2 gives us 11 total for the area of the first trapezoid. And I keep going for the rest of the trapezoids. Any questions on trapezoidal Riemann sums? All right. So I'm going to jump ahead and we'll take a look at some free response questions requiring Riemann sums. I think I'm going to go ahead and save this as a PDF so we can write on top of it. Alright, so here I've got Joanna that's jogging along a straight path for the first 40 minutes. Her velocity is given by a differential equation v. We have selected values of v given in the table above. T is measured in minutes, vt is measured in meters per minute. The first thing they want us to do is to use the data in the table to estimate the value of v prime of 16. I believe we've got Kyle first. So Kyle, how would you estimate the value of v prime at 16? Yep, we're on A. So estimating the value of v prime at 16, what do we need to do? So these are the only values we have and we don't have a formula, so we can't get the midpoint. I'm going to jump to Sarah. Okay. V at 20 minus V at 12 over 20 minus 12. That looks good. So that was our average slope formula. Just y2 minus y1 over x2 minus x1 should give us an estimate for the slope between 12 and 20. So this is going to be 240 over, 240 minus 200 over 20 minus 12. Or I've got 40 over 8. Or 5, as our estimate for the value of v prime at 16. Oh. Kyle, back to you. What would the units be right now? Perfect. Meters per minute squared. Okay, jumping over to Andrew. Using correct units, explain the meaning of the definite integral of the absolute value of Vt from 0 to 40 in the context of the problem. Awesome. Total distance traveled, and you're right, it would be in meters. Okay, integral from 0 to 40 of the absolute value of Vt dt is the total distance Joanna jogged. From t equals 0 to t equals 40 in meters. Okay, Niall, if we did not have the absolute value, then what would this represent instead? Oh, I've lost Niall. So that brings us back to Sarah. Sarah, if we did not have the absolute value, what would this represent instead? Displacement, perfect. So this would be the total displacement that Johanna jogged from t equals 0 to t equals 40. Or how far away she was from when she was at t equals 0 to where she was at t equals 40. Over to Kyle. I want to approximate the value of the absolute value of Vt if we integrate from 0 to 40 using a right Riemann sum with the 4 subintervals indicated by the table. What do we need to do? Okay. Okay. I'm going to zoom out a little bit. So this is the absolute value from 0 to 40 of the integral of Vt dt is roughly equal to. You said 12 times 200? Okay. What's next? Okay, 8 times 240. Okay, we're taking the absolute value of Vt, so this should be 4 times 220, okay. Plus 16 times 150, perfect. Okay. So I'm gonna jump over to Andrew, I think, while I try to do this together. This is no calculator, so you've got to multiply this out. So what is 12 times 200 first? Okay, I've got 2400 plus... Okay, I've got 1920. Tell me if you get anything different, okay? So 880, and okay, I've got 16 times 150. 10 times 150 would give me this, and then 6 times 150 would give me this, right? Okay, then we can add straight across. So I've got 0, 2, 8, 1, 10, 15, 32, 36, 6, 13. Okay, I've got 15,600. Does anybody have anything different? Okay, I do too. So that's 1500 plus 900. I feel like I'm too big here. I think I just added 8,800. So I'm worried about my adding here. Let me do that again really quick. So I'm going to take the 80 from this 880 and throw that into this 1920. So that's 2,000. Plus the 2,400 is 4,400. Plus the 800 I left over here. So that's, I had 4,400. I've lost my place. 4,400 plus the 800. 5,200. Plus 2,400. Okay, I've got 7,600. Can I have someone double check? While we're doing that, okay, cool. Sarah, what should our units be for this? Meters. Oh, sorry, I guess we already answered that, but meters. I'm going to throw that on this line just so you've got room for the next one. So that's 7,600 meters. Okay, for part C, I've got Bob riding his bicycle on the same path. For the first 10 minutes, Bob's velocity is modeled by bt equals t cubed minus 6t squared plus 300, where t is measured in minutes and bt is measured in meters per minute. I want to find Bob's acceleration at t equals 5. Okay, so we've got an equation for his velocity. Sarah, I'm going to go for you again. If this is the equation of Bob's velocity in meters per minute, then how can we get Bob's acceleration at t equals 5? Okay, we're going to derive this. Let me copy this equation really quick. So our b of t is t cubed minus 6t squared plus 300. What happens if we derive? Okay, so I've got 3t squared minus 12t. And then I want to know what the acceleration is at the time 5 minutes after they left. So we'll plug in 5. What happens when we plug in 5? Okay. So final answer is 15. What should my units be? Yes, meters per minute squared. Okay, last one. Based on the model from part B, find his average velocity on the interval from 0 to 10. Kyle, if I'm looking for average velocity, then what do I need to do? What were we given? So what is BT? BT is velocity. So if we have an equation for velocity and I want average velocity, then what I'm really looking for is the average value of BT. So how can I set up the average value formula for BT? Yes. Okay, we're going from 0 to 10, so 1 over, okay, times, yep, which was t cubed minus 6t squared plus 300, and we're going to do that in terms of t. Okay, I'm going to have you keep going. So what happens when I integrate right now? Don't need a plus c because we've got bounds, but I will go from 0 to 10. Okay, and I'm going to multiply all of that by the 1 over 10 that you had on the outside. Okay, if I plug in 0 for my lower bound, everything will cancel, so I'm only concerned about the upper bound. So this is 1 over 10 times everything that happens when I plug this in. Andrew, back to you again. What's 10 to the 4th power? Okay, so I've got 10,000 over 4 minus... Okay, what's 10,000 over 4? 2,500. That's okay, language difference. So what happens when I add all this together? $3,500 divided by 10. 350, awesome. So this is our, we got our average value of BT, so what should my units be for this one? Meters per minute, perfect. Okay, any questions on the first one? Zoom out here. Or anything you guys want me to discuss? All right. Doing one more then. So another no calculator. I've got a train running back and forth on an east-west section of railroad track. Train A's velocity in meters per minute is given by this differentiable function. The velocity of train A at any time, where t is measured in minutes. And we've got some values of that in the table above. The first thing they want us to do is find the average acceleration of the train A over the interval from 2 to 8. So, Kyle, over to you again. Right now we've got a velocity of train A, or at least a table of velocities. How would we go from this to get to average acceleration? Okay, we would want to derive if we had a function. We don't have the actual function, so we're going to have to make an estimate for the derivative. What's another word for the derivative? Or what is a derivative? Okay, we are looking for the average acceleration, but a derivative is a slope. So what we're looking for is the average slope. Right. So go for it. Okay. Perfect. I'm going to rewrite that down here. So our average acceleration, okay, and we'll keep going from there. So Kyle, back to you. What's V8 and what's V2? Okay. All right. Okay, can we reduce that at all? Okay, negative 110 over 3, and what are our units? Perfect. Meters per minute squared. Okay, part B. I want to know, does the data in the table support the conclusion that train A's velocity is negative 100 meters per minute at some point between 5 and 8, and then give a reason for our answer. So let's go Sarah for this one. Okay, so Sarah, we're on part B. I want to know, does train A's velocity at some point between minute 5 and minute 8 have to be negative 100 meters per minute? Yes or no, and why? Okay, yes, you're right. We just have a bunch of points though, so what told you that we had to pass through negative 100? Okay, from 5 to 8, we went from above 100 to below 100, right? Okay, we are differentiable. If we're differentiable, we're also continuous. So we do have a theorem that says as long as we are continuous, then we have to pass through all of the y values from a to b. Do you remember which theorem? That's it. Okay. So for part B, we can say that by the intermediate value theorem, because this function is differentiable, we must pass through all points between 40 meters per minute and negative 120 meters per minute at least once from 5 to 8. So it looks something like this. VA is differentiable, that was given. And therefore VA is also continuous. As VA at 8 is negative 120, and VA at 5 is 40. By the intermediate value theorem, VA must be negative 100 at some time between them. All right, any questions on B? Zoom out. Okay, for part C, Andrew, over to you. At time 2, train A's position is 300 meters east of the original station. The train is moving to the east. I want you to write an expression involving an integral that gives the position of train A in meters from the origin station at the time t equals 12. So what should our setup look like? Awesome. Okay, so it looks something like this. I'm going to rewrite this a little bit bigger down here. The position of train A at any time would be equal to the original starting position of train A at the time t equals 2, plus the integral of the train's velocity from 2 to 8. Andrew, why are there no absolute values for this integral? Right. We're looking for our distance from the original station, which means if the train moves back towards the original station, we will actually lose distance. So I do need to keep all of my negatives negative. Okay. I'm gonna rewrite this really quick from 2 to 8 of VA at t dt. Alright, so they told us to estimate this integral somehow. We're going to estimate this integral using a trapezoidal Riemann sum with 3 subintervals indicated by the table from 2 to 12. So I'm going to bring us over to Sarah. I want a trapezoidal Riemann sum with the 3 subintervals from 2 to 12. How could I set up our equation for the area of the first trapezoid? Perfect. Okay, and I'm going to keep doing that for the other 3 trapezoids. Okay, so I'm going to zoom out here. The integral from 2 to 8 of VA t dt was roughly equal to three by 140 over 2 plus 3 by 40 minus 120. Negative 80 over 2. Plus 4 by negative 120 minus 150, or negative 270. Put this down again, so I keep writing on the screen and pushing the screen back as I write on it, but 270. Oh, that's much better actually. Okay. So if we integrate this, we'll get this for our trapezoidal Riemann sum. I'm going to divide really quick. So this is 140 over 2 is 70, times 3 is 210. I've got negative 40 times 3 is negative 120, and 270 divided by 2, I've got negative 135 times 4. I'll leave that, I think, negative 135 by 4, so that's 214, 5, negative 540. So this is negative 90, and the negative 540 is negative 630. now, negative 450. Going the opposite way. Alright, so I've got to go back and substitute then, since this is the integral from 2 to 8. So if I take this and substitute, then our position at 12 should be equal to 300 minus 450, or negative 150. Sarah, over to you one more time. What are my units for this? Meters, right. So we are a negative distance in meters. Originally we started 300 meters east of the station. So if we started where positive was east and we ended up at negative 150, then where did we end up? Were we east of the station or west of the station then? Sarah, if we were at negative 150 meters, were we east of the station or west of the station? West, perfect. West of the origin station. All right, last one. For part D, we've got a second train, train B, traveling north from the origin station. At the time t, the velocity of the train is given by this velocity, and at time 2, the train is 400 meters north of the station. I want to find the rate in meters per minute at which the distance between train A and train B is changing at time t equals 2. Okay, Andrew, over to you. The equation of the train is not given, no. Let me draw a picture really quick first. We'll see if that'll help. So we were told that train A, which I'm going to draw here in green, is going from the origin station, starting east of the origin station. And it went a little bit to the right because it had positive velocity, and then eventually went to the left until it went past the train, right? Past the original station. Train B is traveling north from the original station. what we want to find is the rate in meters per minute at which the distance from train A to train B is changing at the time t equals 2. At the time t equals 2, we had positive velocity from 0 to 100, which means we should be still to the right of the station. So our distance between train B and train A would be this black line here. Okay, so if I'm looking... Pythagorean Theorem. Okay, so to use Pythagorean's Theorem, this distance I'm going to call z. This distance I'll call x, and this distance I'll call y. So we could use Pythagorean's Theorem with z, x, and y and solve for z, which means we do need to find a way that we can get the distance at x at the time t equals 2, and a way we can get the distance of y at the time t equals 2, where y is the distance b is traveled and x is the distance a is traveled. You've already given me earlier a way that we could get the position of train A using Riemann sums. Actually, we were told to position it 2, I think, directly. Yeah, our time to our train A's position is 300 meters east of the station. So we know x is 300 exactly at this time. But we do need a way to get train B's position at the same time. And the velocity. What's train B's position at the same time? Okay, 400 meters north of the station. Perfect. Okay, so I'm going to define some variables. We'll redraw our picture really quick. So x... well, sure. X is equal to the position of train A at any time. Y is equal to the position of train B at any time. Z is the distance between trains. Okay, then we've got our triangle one more time here. Okay, so Pythagorean's theorem you said, so we'll set that up first. Z squared equals y squared plus x squared, where right now y is 400, you said. X is 300. Pythagorean triple, what should z be? Yep. 3, 4, 5. So this should be 500 meters is the current distance between the train at the time t equals 2. Okay, but we can also take this, so we need to figure out how fast the distance is changing and derive it to get times. I'm going to jump over to Kyle. So for Kyle, if we derive this equation in terms of time, what happens? Okay, that all looks good. We don't know what dz over dt is, but we do know z, x, and y right now, and we've got equations for how fast the trains are going in the y-axis in a table that gave us how fast it's going in the x-axis. So let's fill in everything we know so far. Kyle, sticking with you for a minute. How fast is train A going at 2 minutes? $100. Okay, so dx over dt is 100 at the time 2. dy over dt is vb at t, which is given as negative 5t squared plus 60t plus 25. So at the time t equals 2, what's going to happen? Okay, Kyle, still with you? Don't need to divide the whole function by 2. This is just plugging in the time t equals 2. So not actually multiplying here. So I've substituted t for 2. What's going to happen here? $125, okay. Alright, so train B is traveling at 125 miles an hour north. So we can plug in all of our values we don't know, or all the values we know, and solve for all the values we don't know. Oh wait, you were talking about up here, weren't you? Okay, I can divide by 2 for everything up here. Sorry. So this is z, that's 500. I think I'm going to write the 2 and we'll cancel it in a second. So 2 by 500 by the dz over dt, we don't know yet. 2 by, we are at 400 at 125 miles, or meters per minute. 2 by 300 at 100. Okay, so at this point, I'm going to divide everything by 200. So that'll leave me with 5 times dz over dt equals 4 by 125 plus 3 by 100. What's 4 by 125? Not dx, dz over dt. Okay, so I've got 800 you said. What's 800 over 5? Dz over dt. Not 160, sorry. Yep. Okay. So we've got 160. What are my units? meters per minute. Perfect. Sorry, 160 is what you said the first time. My bad. All right. Any questions on anything from this one? Okay. So I'm gonna stop there for Sarah. Thank you so much for coming. If you want to come next time, let me know if you've got topics that you want to talk about for the AB session. I'm gonna keep Andrew and Kyle for another one more FRQ, I think. Or any questions in the homework you guys have. So thank you so much, Sarah. Goodbye. All right. So first, do either of you have questions on the homework that you want to go over? And if not, I can jump into a different FRQ. Oh, that's okay. 23 multiple choice section 2. Okay, let me pull this up. So see. CBC practice test 2 from Baron. Okay, let me know if I've got the wrong file. You said 22 in the multiple choice, right? Is this correct? Okay, cool. Let's see. I've got the derivative is y over x. X is greater than 0, y is greater than 0, y is 3 when x is 1. Oh, sorry. Okay, solid is cut out of a sphere of a radius 2 by 2 parallel planes, each 1 unit from the center. What is the volume of the solid? I've got something like this. X squared plus y squared equals 4 at the center of our sphere for this circle. This circle has an x and a y plane, right? Okay. And then for our greater sphere, I'm going to cut two planes that we want to be able to spin to. That would look like this. So the way that I've cut this now, I'm going to change our x and spin a radius for our y from wherever y is to 0. From x equals -1 to x equals +1. So that's going to look like this. In terms of x. Okay, my r1 is my distance, my change in my y values. But because that needs to be in change in x, we'll have to solve for y using our equation. So y squared is 4 minus x squared. Since I'm squaring my y already, I can substitute that in. So I've got pi times the integral from -1 to +1 of 4 minus x squared in terms of x. Okay, and then what that does is that spins this space out and keeps spinning that space out as y gets bigger and bigger to give us all of this shape. from -1 to +1. Nah. This whole radius, when I spin this out, is still going to spin out that circle. Okay, that still does work. Alright, so if I integrate this then, this is going to give me 4x minus x cubed over 3 times pi from -1 to 1. From -1 to 1 is just going to double whatever I get, right? So this is 4 minus 1/3. I've got 11 thirds, 22 thirds pi, which is the alright. Checking there's okay, they did this in terms of y instead. Alright, we still didn't quite do it the same way they did, but we're close.